Hi, welcome to the Interpreting Electric Meter Data series of presentations sponsored by Better Bricks. This training is broken down into 5 parts, and this is part 2, What is your energy bill all about? In this session, we're going to be discussing different terms that you'll see on your energy bill, including real and reactive power, demand, energy, power factor. We'll talk a little bit about the mathematics of electricity, and charges that you would expect to see on your electric bill. We're going to start with energy terms. The first energy terms we're going to talk about here is energy. And energy is defined as the ability to do work. In the electrical sense, we measure the energy in kilowatt hours. 1 kilowatt hour is the energy expended, for example, by a 1,000-watt load over the course of 1 hour. Now, real power or demand is the rate at which energy is being consumed. It's measured in kW, which is kilowatts. Most utilities refer to demand as a value reference to an hourly usage rate. Reactive power, or reactive demand, is measured in kVAR, kilovolt amps reactive, and reactive power is power associated with magnetic fields in motors, transformers, and capacitors. Later on, we're going to describe this in the water tower analogy. Suppose you want to fill a water tank with water, and the only way you can do it is by climbing up a ladder, carrying a bucket of water, and then dumping it into the tank. You then have to go back down the ladder to get more water. Now, strictly speaking, if you simply go up a ladder, not carrying anything, and come back down, not carrying anything, you've not done any work in the process. But since it did take work to go up a ladder, you must have gotten all that energy back when you came down. Well, you may not feel that coming down the ladder completely restores you to the condition you were in before you went up, but ideally from an energy conservation viewpoint you should. If you don't agree, you can get out your physics book and check out the official definition of doing work. Okay, if you still don't agree that walking up a ladder and coming back down doesn't require any net work, then think of it this way. Would you pay anyone to walk up a ladder and back down without doing anything at the top? Probably not. But then if they dumped a bucket of water in the tank while they're at the top, then that would be something worth paying for. When you carry a bucket of water up the ladder, you do a certain amount of work. If you dump the water at the top and carry an empty bucket back down, then you've not gotten all your energy back because your total weight coming down is less than going up, and you've done work during that process. The energy that it takes to go up and down a ladder carrying nothing either way requires reactive power, but no real power. So the energy that it takes to go up a ladder carrying something and come back down without carrying anything requires both real power and reactive power. So in this sense here, the water and the amount of energy that you're expending to bring that water up to the top of the tower is your real power, and your reactive power is the energy that it takes to go up and down the ladder. It's the same principle in electric motors. You have an electric field in motors, and those motors, that electric field isn't doing any work until you have rotation of the motor. So it's in the wires and in the magnetic fields. That's the reactive power when we're talking about electricity. Okay, when we talk about the description of a power system now, we can talk about the reservoir as being the generating plants because we have the power stored up in the water tower as in this example. And the poles and the wires are the ladders, the buckets, and the person. So the more poles and wires you have, or the more people you have going up and down the ladder, or the bigger the bucket size, the more water they can carry, is in relation to the size of the wires. So that'll be important when we talk about some of your energy charges later on. When we talk about watts, we need to use some bigger terms. So a kilowatt is 1,000 watts. A megawatt is 1,000 kilowatts. So let's say, for example, you have a 1,500 watt heater, which is the same as a 1.5 kW or kilowatt space heater, and it runs constantly for 2 hours. You will have used 3,000 watt hours of energy, or 3 kilowatt hours. So the formula for that is 1,500 watts times 2 hours times 1 kW for 1,000 watts to convert it into kilowatt hours. One thing to note, if your heater is being controlled by a thermostat, so it cycles on and off to maintain a certain temperature, you're going to be using less than that 3 kilowatt hours for this period of time. It's going to depend on the amount of time that it's cycling on and off. That's one reason we need to measure with meters and collect interval data because you just can't do a calculation by just taking a sample period of time and saying, here's how much energy I'm using. We're going to talk about energy calculations, and first we're going to show you a load profile that's showing the demand in kW versus the time. Now this is for a commercial office building. So between midnight and about 5 a.m., the energy is between about 300 and 400 kW. From 5 a.m. to around 11, the usage varies between 300 and 1,000. At just before noon, this is probably an extra load coming on, probably a second chiller to cool the building down, part of the heating and ventilation system. So that load starts, and then it runs at about 1100 kW until about 5 p.m. And then at 6 p.m., it drops off. So the heating and ventilation system and most of the lighting has been turned off. And then the load slowly trickles down till it's back to its base load of between 300 and 400 kW. Now if we take a look and try to calculate the kilowatt hours being used, that's going to be the area under this curve. So we can calculate that by taking an average of about 350 kW times 5 hours. And let's just call this an average of about 700 kW for the next 6 hours. And then from 11 to 6, so another 7 hours of approximately 1100 kW. And then we'll average this back again here at about 450 kW from 6 to midnight. Now, totalizing all those sections up, you can calculate what the total kilowatt hour is used during this period of time. So the number of kilowatt hours and the demand are two important things that are going to show up on your electric bill. One thing people want to know is, when do they peak? They'll see on their electric bill that they've reached a value of a certain number of kW, and they're charged for that kW. A load profile such as this one would show you that that largest peak happened on this particular day anyway, at about 4:30 in the afternoon. Now this is just one day, and your electric bill covers a longer period of time than that, certain number of days of service. And so you would need to look at a profile that shows the whole month to find out when that actually happened.